Hello and welcome to this Pelham Smithers Associates Guide. This presentation is to explain the technology behind Japanese hardware startup Ballwave. Called BallSaw, the technology enables us to measure elements in the air with a substantially greater precision than before. BallSaw technology takes advantage of the diffractive properties of waves, specifically the diffractive properties of a certain type of wave, the surface acoustic wave or SAW, on spherical objects. We obviously associate waves with the sea, while anyone who has thrown a stone into a pond will have both created waves and seen diffraction at work as those waves dissipate over distance. Waves have two useful features. The first is that the two separate but identical interactions both create the same wave. And the second is that they are relatively straightforward to measure. There are three key measurements: the amplitude, which is the height of the wave, the wavelength, which is the distance from one wave to another, and the frequency or the time element, which is the time to complete one oscillation or the number of wave crests past a fixed point per second. Surface acoustic waves, or SAWs, are a certain type of wave that are particularly good for precision measuring, because the exercise of measuring such waves doesn't impact the wave itself. The best known surface acoustic wave is the earthquake or seismic wave, but SAWs are also usually used widely as a means of capturing data to our phones from radio waves. To create a SAW, you need an elastic material for the SAW to travel on, an excitable material such as two near-touching electrodes called an interdigital transducer or IDT, and a means of exciting the IDT, i.e. an electrical current. Once you create a SAW, it travels along the surface of the material until it has diffracted so much that the wave has been reduced to zero. So what is this diffraction? Diffraction is the process of reverting a system to equilibrium along the lines of every action has an equal and opposite reaction. In the case of waves, it's the process of evening out through backfilling the areas already affected while absorbing the wave into new neighbouring territories. The process begins after a certain distance, which is called the Fresnel distance. Critical to measuring items is often to get the Fresnel distance extended. One way to do this is to eliminate it completely. This you can do on a spherical material, because depending on the starting size or aperture of the excitement, diffraction varies in form. Smaller apertures produce thinner diffractions and after a point invert. Importantly, there is a specific point, approximately 8 degrees, where the wave doesn't diffract at all, instead collimates. In such a scenario, the wave doesn't die away but keeps going. Now on a spherical surface, what this means is that it keeps going round and round. Now it should be pointed out that there eventually is loss due to friction, but it is nugatory for our purposes. Now, as mentioned, every type of interaction has a unique wave signature, but this also means that differences between wave signatures can be minute. Identifying such minuteness over short distance, such as a single revolution, might be very difficult. But with zero diffraction, we can measure over, say, 100 revolutions, at which point the wave signature becomes very clear. So what does this mean in practice? To create what we call the BallSaw, we take a tiny 3 mm diameter ball of quartz and print a tiny electrode on it, roughly 0.2 mm in size, which is the 8 degrees aperture. The sphere needs to be as small as possible, so that each rotation takes as little time as possible. Onto that sphere, we spray a material designed to react to the item we want to sense. This material will vary from one product to another, so you'd have amorphous silica for moisture, or antibodies for viruses, or palladium platinum film for a specific gas like hydrogen. The process is electrified, creating the SAW. Should the material being targeted touch the interactive material, that would then create a new SAW, which would have the properties we were looking for. Here is such a BallSaw in real life. You can see the sphere, which is connected to an electric circuit, which in turn can be attached to a motherboard. This early prototype is around 5.5 centimeters in length, or just over 2 inches. So it's really small, enabling the creation of handy palm-sized measuring devices. That then is the technology behind Ball-Wave's ball saw. It's so precise that it can measure hydrogen at just 10 parts per billion, which is what you need for EUV semiconductor production, and should be able to detect the presence of viruses in a room, or if food is going bad. Indeed, the list of potential uses of this technology is as wide as it is extensive. Thank you for watching.